As we near the second anniversary of the James Webb Space Telescope's launch, its first 20 months of scientific operations have significantly reshaped our understanding of the universe. However, the telescope is also presenting serious challenges for scientists by uncovering inconsistencies in our cosmological theories. The precise timeline of when initial star clusters formed into the early galaxies we observe today remains unclear. While cosmologists once believed this process gradually unfolded within the first few 100 million years after the Big Bang, the James Webb Telescope's discoveries are forcing a re-evaluation of these assumptions. Currently accepted theories propose that these early proto-galaxies matured 1 to 2 billion years into the universe's existence, forming dwarf galaxies that merged and grew into larger ones like our Milky Way. The cosmic dark ages were believed to be a period when the universe was shrouded in a fog of neutral hydrogen, trapping the light from the first stars and galaxies. According to the Standard Model, this fog lifted about 1 billion years after the Big Bang, as neutral hydrogen became ionized and dispersed. With the end of the Dark Ages, the first stars began clustering into galaxies, gradually shaping the universe into what we observe today. That's what our models indicated, nearly all of them. Then, the James Webb Space Telescope was launched, and suddenly, we faced a conflict that could redefine our understanding of the cosmos. The discovery of thousands of unusually bright early galaxies by Webb, some even similar to our own, astonished astronomers. This finding cast serious doubt on our fundamental understanding of how the universe evolved. For these galaxies to shine so brightly, they would have needed to grow to enormous sizes in an unusually short time. Typically, a galaxy's brightness correlates with its size, but these galaxies emerged during cosmic dawn, not long after the Big Bang. How could such massive galaxies have formed so rapidly, and how are they so bright when, theoretically, they shouldn't even exist? Scientists have coined the term too big and too soon for these galaxies. Their brightness suggests they should be as massive as galaxies like the Milky Way, but these early galaxies formed in a fraction of the time. This anomaly has left scientists puzzled, prompting a re-evaluation of fundamental cosmological principles. Acknowledging the need for thorough investigation, a team of researchers turned to supercomputers, recognizing the limits of human understanding in this complex scenario. To unravel the unusual brightness of these galaxies, they created a galaxy formation model and ran simulations on supercomputers. These simulations mirrored the early universe's gas dynamics, showing how it coalesced into stars and formed galaxies. By carefully analyzing the universe's mass, energy, momentum, and chemical composition, the researchers proposed a possible explanation. They suggested that stars in this early epoch may have formed in sudden, intense bursts after long periods of inactivity, called bursty star formation. This differs significantly from the steady star formation rate seen today. The researchers believe this process could explain the early universe's extraordinary brightness. Consequently, the team concluded that the bright galaxies observed by the James Webb Space Telescope in the universe's early stages might result from these bursts of massive star formation, which could explain their higher luminosity compared to what was expected. Essentially, the universe experienced a sudden "let there be light" moment. When Webb commenced its science operations in the summer of 2022, its deep observations began revealing high redshift galaxies. These galaxies, seen as they were when the universe was less than 400 million years old, appeared more luminous than predicted by the standard cosmological model. This discrepancy led to claims that the Standard Model, which describes galaxies starting small and growing through mergers driven by dark matter filaments and halos, might be incorrect. The simulation results suggest that a galactic system doesn't need to be exceptionally massive. If star formation occurs in bursts, it will emit bursts of light, explaining the presence of several very bright galaxies. Crucially, the new simulations align with the hierarchical growth model of galaxies outlined in the standard cosmological model. However, the issues with the standard model don't end there. The James Webb Space Telescope has highlighted several significant flaws in our existing theories. Number 1. Extremely early galaxies. In cosmic terms, a galaxy forming only a few 100 million years after the Big Bang is almost instantaneous. The Big Bang occurred about 13.8 billion years ago, and models predicted that galaxies did not form for the first billion years. Yet, the James Webb Space Telescope has upended this notion. It has identified fully formed, massive galaxies at the universe's edge. The oldest galaxy discovered so far is Macy's galaxy, which existed when the universe was just around 390 million years old, remarkably young in cosmic terms. Macy's galaxy is among several candidates spotted by Webb, with further research potentially uncovering even earlier galaxies. Number 2. Scientists have discovered a massive collision very early in the universe. Just when cosmologists thought they had a solid theory for the timing and nature of galaxy collisions in the early universe, the James Webb Space Telescope presented a challenge. This challenge involves a collision of two massive galaxy clusters that merged into a colossal galaxy cluster. This occurred when the universe was only half its current age, which, according to our cosmic model, is too early. The result is the El Gordo galaxy cluster, and its existence challenges the Big Bang model, which posits that galaxies form first and then merge to create larger structures over time. The appearance of such massive collisions early in cosmic history raises questions about whether we need a new model or revisions to the current one. Number 3. Giant black holes near the universe's birth. The James Webb Space Telescope, observing young galaxies as mere red specks, detected an unexpected number with intense activity at their centers. These galaxies, with cyclones churning in their cores, suggest an abundance of large black holes weighing millions of suns, stirring the surrounding gas clouds. These black holes are likely the precursors to the supermassive ones that appear prematurely in the cosmic record. By studying these early black holes discovered this year by Webb, scientists aim to uncover their origins and determine if they grew rapidly or were born massive. Surprisingly, instead of finding many smaller hungry black holes, Webb revealed a series of large ones that could challenge our existing theories of star and galaxy formation. Number 4. Missing heavy elements. The Webb telescope not only found extremely massive early galaxies, but also revealed that these galaxies defy existing rules. Astronomers use JWST to look 12 billion years back and study galaxies and their historical rules. The most surprising finding was that ancient galaxies produced far fewer heavy elements than predicted based on later galaxies. This discrepancy was previously undetected because earlier instruments couldn't analyze the chemical composition of such distant galaxies. The James Webb Telescope, however, enabled observations just a few 100 million years after the Big Bang, uncovering a break in the expected relationship between star formation, mass, and chemistry. The James Webb Telescope is expected to operate for another decade or two, potentially revealing intricate details about the universe's origin and addressing many current unanswered questions. What are your thoughts? Share your comments, and don't forget to subscribe to SpaceBeat News.